Hello, I'm Bruce Hemp, Applications Section Leader for HF Products here at Linear Technology. Today I'd like to introduce the LTC 5586, a wideband, high linearity IQ demodulator with IF amplifier. This device is like no other IQ demodulator on the market. It features greater than 1 gigahertz IF bandwidth and over 20 register fields that can be programmed through SPI to customize the device to the individual application for industry-leading accuracy and performance. Let's look at the block diagram. Here we see the basic LTC 5586 architecture consists of an IQ demodulator with an RF switch and attenuator at the front, with internal LO buffers and programmable LO impedance matching network, and integral dual DC to 1 gigahertz output amplifiers, each with 0.5 to 2 volt common mode output voltage, designed to directly drive a dual ADC. The RF inputs are internally matched for 0.5 to 6 gigahertz continuous coverage with better than 10 dB return loss. There is provision for external differential baseband filtering after the mixers to suppress high-frequency mixing products in order to achieve best IF amplifier linearity. The LTC 5586 is designed to support the wideband observation receiver function for a DPD power amplifier. The input RF switch can be used for linearization of more than one transmit PA, as we see here, or for built-in test purposes. The RF attenuator helps the system achieve the best overall combination of linearity and sensitivity. The device is also well suited for wideband receiver applications, such as point-to-point microwave radios, as we see here, or software-defined radios with system bandwidth up to 1 gigahertz or more. For best performance in either of these applications, low demodulator error is very important. Quadrature phase error and gain imbalance are often the two largest contributors to error vector magnitude, or EVM. In the past, if your system had a gain imbalance, the system designer would reduce the error by trimming a VGA, scale one of the system ADC outputs, expend DSP resources or FPGA resources to correct digitally, or simply accept the error as is. Quadrature phase error is more difficult to correct because the system designer must implement corrections to the ADC outputs that are more complex, beginning with an estimation of the quadrature phase error, and then use a sine-cosine lookup table to determine the proper IQ scaling coefficients. It can be done, but it's going to consume some extra DSP slices or FPGA resource blocks. Now consider the LTC 5586. It has an initial gain imbalance error of only 0.06 dB typical, with a SPI gain imbalance adjustment range of plus or minus 0.5 dB and 0.016 dB steps. You can easily trim out the IQ gain imbalance of not just the IQ demodulator, but the whole IQ receive signal chain. The LTC 5586 quadrature phase error adjustment capability is similar. You no longer have to settle for whatever phase imbalance the IQ demodulator provides. With a typical adjustment range of plus or minus 2.5 degrees and 0.05 degree steps, the quadrature phase trimming task is simple. If left untrimmed, the quadrature phase imbalance is a respectable 1.1 degrees, but for system designers willing to take the time to adjust down the error, it will mean improved EVM accuracy for DPD power amplifiers or improved receive SNR for RF and microwave receiver applications. For the most demanding high-accuracy applications, the LTC5586 also provides adjustable cancellation of several other sources of error: DC offset, IM2, IM3, HD2, and HD3. These undesired products can all easily show up within the passband of the IQ baseband, so filtering is not an option. In the power-up default state, the LTC5586 DC offset, IM, and HD performance is quite good. But for the purists, the results can be made better by making lease-in system adjustments, thus providing the best possible EVM or SNR depending on the application. Finally, in these last two illustrations, we show excellent performance before any SPI adjustments are made, and even better performance for those applications where proper SPI adjustments are applied. In this figure, before the adjustments, we see image rejection of 38 dB. Not bad, but after quadrature, gain, and phase mismatch adjustments, we see image rejection improves to 72 dB. We can also see that with proper adjustments, IM3 has dropped about 3 dB, IM2, some indifference, have dropped at least 10 dB, and HD has dropped at least 2 dB. After adjustments, what we are left with is a very clean baseband output spectrum, where the largest remaining in-band spurious component is the image, which in this case measures minus 72 dBc. In summary, the LTC5586 offers outstanding performance for wideband IQ demodulator applications. For further information, please visit our website at linear.com. Thanks for watching.